All right. So, we've just learned about limits at infinity back in chapter 4. We're going to jump ahead for one section into chapter 5, section 5.6. I have no idea why this section is in chapter 5. It doesn't make sense to me. Because this section called L'Hopital's rule, this is a section all about application of differentiation to limits. So we're going to learn how to calculate some tricky limits using a strategy that involves derivatives. So first of all, let's talk about indeterminate forms again. All right, let's look at this example. F of x equals e to the x minus 1 all over x. First, I want to look at the limit as x approaches 0 of this function, e to the x minus 1 over x. All right, e to the power 0 is equal to 1. And so the numerator is going to be approaching 1 minus 1, which is 0. The denominator is also approaching 0, of course. So we can, I'm going to sort of informally write an arrow, and then this is 0 over 0. This is an indeterminate form. Okay, when our numerator is approaching 0 and our denominator is approaching 0. That is an indeterminate form. It doesn't tell us anything useful, right? That doesn't mean that the limit is 0. It doesn't mean that the limit's undefined. I don't know what the limit is. We're going to figure that out later, okay? But my point is the indeterminate form. If we look at the limit as x approaches infinity of this same function, we get another indeterminate form. Because e to the power, as x approaches infinity, e to the power x is going to be also approaching infinity, minus 1, and you still are approaching infinity. So this whole numerator is approaching infinity. And the denominator is, of course, approaching infinity. So this is infinity divided by infinity, which is another indeterminate form. So when you have a function of the limit of a function that is in one of these indeterminate forms, specifically 0 over 0 or infinity over infinity, we can apply a rule called L'Hopital's rule. Let me tell you a little history. L'Hopital, which, by the way, this is just the word, his name literally just means the hospital. This is the word for hospital. This is French for the hospital. So L'Hopital was a sort of an amateur mathematician who was learning calculus. He was honestly just a rich dude who liked math and wanted to kind of make a name for himself and go down in history. So L'Hopital hired a tutor for himself. L'Hopital hired a mathematician named Bernoulli. There were lots of different Bernoullis, by the way. There were several different Bernoullis. I think they're related to each other. And this was one of the Bernoullis. And so Bernoulli did some research and taught L'Hopital a bunch of stuff and basically helped L'Hopital write a textbook on calculus, which was L'Hopital's sort of grand goal. He wanted to write a textbook on calculus, which he did. And actually L'Hopital's calculus textbook was very influential. So we owe L'Hopital quite a bit for that contribution. But during the time that Bernoulli was working for L'Hopital, Bernoulli figured out this theorem. Bernoulli figured out this thing about limits and derivatives and proved it. But because Bernoulli was working for L'Hopital, and L'Hopital published the textbook under his own name, this went down in history as L'Hopital's rule, because it was first seen in L'Hopital's calculus textbook, despite the fact that it was actually discovered and proved by Bernoulli. So let's write history here. Let's write this wrong and refer to this now as Bernoulli's rule. No one will ever know what you're talking about if you call it Bernoulli's rule. And I also probably spelled Bernoulli wrong. But no one will know what you're talking about. But we know that Bernoulli actually is the one who deserves the credit. All right. So it goes like this. First of all, you need two functions, and they need to be differentiable. If not at, near c, which is going to be some value. This could be infinity. Okay. If, as x approaches c, the ratio f of x divided by g of x, if this is approaching one of these indeterminate forms, 0 over 0, or the ratio approaches infinity over infinity. So if we have a ratio of functions like this, like a quotient, if it's in one of these indeterminate forms, then the limit as x approaches that c of that ratio, f of x over g of x, is going to be actually equal to the limit as x approaches c of f prime divided by g prime, the derivatives of those functions. So the ratio of functions and the ratio of their derivatives turns out to have the same limit, but only if it's in one of these two indeterminate forms. Okay, if it's not in an indeterminate form, then this equality is not guaranteed. Okay, it's only in this situation that it's going to work. Okay, so turns out this is super useful because when you differentiate something, often it gets simpler, especially when you're dealing with like power functions and the power goes down by 1, or like a derivative of a log function gives you 1 over x. Things get simpler often when you differentiate them, or at least if not simpler, they get different, which is key. Sometimes the ratio of functions is in an indeterminate form, but the ratio of its derivatives is not. And by the way, this can be chained together, and if possible, if this is still indeterminate, then it's going to be equal to the limit of the second derivatives. But only if it's still indeterminate, only if it's still in a 0 over 0 or infinity over infinity situation. So it's possible that you may have to chain it and like do the L'Hopital's rule multiple times before you get to something that you can work with. So let's look at some examples in the next video.